palestra será a representação de estruturas complexas. Ele vai apresentar os desafios e soluções atuais para a materialização digital. Esta forma matemática de representar a natureza pode ser um agente viabilizador para o projeto computacional de órgãos e tecidos humanos. O Turlif, ele há 20 anos pesquisa tópicos como computação volumétrica, materialização digital, que consiste de uma representação matemática da complexidade da natureza e representação por função. Ele é diretor da empresa Forma, na Noruega, articulador na formação do Digital Materialization Group e integrante de grupos de pesquisadores nesta área na Noruega e no Japão. Tem estado conosco pela terceira vez no Brasil e mantém contato permanente com o nosso grupo de desenvolvimento de hardware e software.
Hello, tudo bem? I would like to thank Dr. De Silva, CTI, and the entire CTI team for having us here. It's a real pleasure. This is my second time to this facility, so I'm a big fan of Brazil. Today I'm going to talk a little bit about some of the informational issues that are involved with trying to actually capture real things. When I say real things, I mean even nature. So biological objects, natural objects, objects in the real world, where we really want to understand the structure of the object and put it inside the computer. So I'll talk a little bit about that. I'm representing basically sort of I have three hats on probably today. One is as a researcher with DMG. I'm finishing my PhD. So Digital Materialization Group, where we've been working for nearly 20 years now on representing how to go about representing real stuff in a computer, how to turn it into information, three-dimensional objects. And also CGPL, which is an open source license, and we've got an organization around that, Common Good Public License. And our goal is to actually make an open source license for the future that deals with these issues of fabrication, deals with these issues of information, being able to cross the boundary between reality and back to information. If we've got that kind of power, it's a lot of responsibility. We should probably have some agreements about how we're going to use it. It's a lot of, yeah. And Euphoria, which is our startup company. And let me see if I can, so just to give you guys an idea of where that's at. So we are located here above the Arctic Circle in Norway. It's a strange place, I guess, to have such a startup. And if I keep zooming in, so you can see there's lots of fjords. And we're on this little teeny island here. Right now it's 24 hours sunshine. So, and in the wintertime it's dark and very snowy. So that's where our startup is. And what we're doing is we're turning some of the stuff that I'm going to show you today into a product that's usable, hopefully. And you'll get to see that a little bit later if everything goes well. I'm doing something you're not supposed to do in a presentation, which is give a live demonstration of software. You're never supposed to do that in a software presentation, but we'll try it today. So I've got some sort of background slides, but I think I'll just probably move through them quickly due to time. It's sort of some of the philosophical concepts behind it. The idea that humans have always worked towards trying to control their environment, and we even label various periods around the materials that we gain control over. So Stone Age, Bronze Age, etc. More control over time. And in the 20th century, we really started to talk about control of the atomic scale, right? That's what the atomic bomb was about. We're now growing diamonds, although maybe not explicitly, but that's probably around the corner. And we're all here talking about biofabrication. So we've worked down towards really, really minute and small scales. And more importantly, with every single kind of technology, first you have to have the information. You have to have the ability to control that technology at a sort of informational level, if you will, or be able to have a way to communicate about it. And if you're talking about information, or if you're talking about control at a very small scale, it means you've got a lot of information you've got to process. So that means your information is going to have to fundamentally be different. It can't be stone tablets. So this is a vacuum tube, so information at the atomic scale. And when I say that, in some sense, it's really the first thing that we really actually started to explicitly have control over in some ways at that scale. Because you're talking about moving around electrons and photons, right? So in a very organized, very controlled manner to get exact outcomes that are reliable. So you could say maybe it's the electron 3D printer or something. So scale matters. And to give you just an idea of that, this is Babbage's first attempt to make a computer, long before the vacuum tube. And this was the idea of the of computation, Alan Turing. So Babbage tried to do a sort of primitive version of this with this machine, and he couldn't. Because he needed really at least an order of magnitude smaller in his tooling in order to acquire the computation he was after. So the machine never ran. So along comes Shannon with his theory of information. And basically, he started moving around electrons and photons and the gates required for that. And you add that with Alan Turing's ideas, and suddenly we have the age of information. We have control over this stuff. So again, the scale, this is an example of how the scale really matters and how we get to where we're at today. And so if you take a look at that in another way, you can even look at information. Here we have stone tablets, books, and silicon little chips, and sort of exponential size drop, exponential gain, even more than in terms of the amount of information you can carry around. What's that have to do with what we're talking about today, and what's that have to do with BioCAD or biofabrication or computer-aided design? So nature sort of participates in this sort of complex, heavy computation all the time at this really fine scale. What we've done, and it was actually a gift probably, otherwise we wouldn't be here, is we were able to simplify that. I'm able to look around in the room and identify this as a laser pin or something, right? I understand the boundaries here. And I can simplify that and draw a sort of contour around it, right? So we've drawn in the sand for a long time, and we've always drawn these contours. And we've gone through the trouble of even purifying materials in our manufacturing processes and then pushing them into really sort of simpler or light computation compared to nature in some sense, in terms of the complexity of the objects we make. Even the very complex objects that we're making today that we put back in the body. You can imagine, I mean, compared to what we're talking about with biofabrication, this is a very simple device. And probably not what you want in your body, right? So the fourth epoch of the digital age is what I call it. Maybe that's a little bit flamboyant, but I sort of see three phases we pass through. The final phase is sort of reaching out of the computer and controlling more than electrons and photons. We're now talking about controlling matter. And Evan's machine here is a great example of that on a personal scale. Going way back, there was processes that were subtractive initially, so you could just put a block of material in and remove something very accurately. But now we can add stuff. That's really important. And we can do it at finer and finer scales. So we have access to complex and heavy computation because we've built these devices that can handle it where we couldn't. And so they can start to compete with nature, this vacuum tube over here, or some of the chemical computation we've been doing. So it doesn't have to be through a computer. Maybe we purify the materials, maybe we don't. And in any case, we start to head towards real tissue, for example, that we're talking about today. We start to head towards putting back, really interfacing with nature for the first time. So the dream that everybody talks about is this. This is kind of pushing the envelope, but the idea that we have this sort of replicator or we have a molecular assembler. And Earl Grey hot, right? This is what Jean-Luc Picard always asks for in the Star Trek Enterprise. And a cup and a tea appears. The funny thing about this is we're pretty good at explicitly making the cup. We still really can't make the tea. But maybe that will come. But can we even do this? Let's step back for a second. This is our world. It's complex. It looks like this, more or less. Even if you have a steel ball, there's a lot going on inside of it. When we look at CAD today, that's how we represent it. Now we might paste that picture that I just showed you on the surface of that, But there is nothing similar between those two things. So the information in the system is fundamentally incorrect. You can't represent reality this way. There's no way to do it. I'll give you another example. Today, in CAD software, more or less, if you were to design a watermelon, this is the best that you, okay, you could spend more time and try to draw some veins in here and stuff with NURBS, but more or less, if you're trying to do it within a reasonable time frame, this is more or less what you would develop, okay? That's a watermelon in CAD. Well, this is a watermelon in reality, and they're nothing alike. They're very, very different, okay? 3D printers today, though, have the ability to print at very fine resolutions. The Objet printer, which is a multi-material printer, can print down to 16 microns per layer, Z-step. So you could start to achieve structures like this, but we can't model them. So currently the hardware, the 3D printing hardware, outstrips the software, effectively, in many ways. Not entirely, but that's more or less the story I'm telling today. And that hasn't really happened since the inception of the personal computer, which is also interesting to note. Okay? When the personal computer arrived, it could do lots of stuff, and there wasn't software to really use it. And then software came along and started leading, and it's led ever since. Software is always leading hardware, typically. So we're back in that state today when we talk about 3D printing. So what are the issues that surround this in terms of, here's some of the main ones for representation. So we have hundreds of megabytes of polygons. So size and processing is a huge issue in these systems. If you do something very simple like the sphere I showed you, that's fine. If you want to do microstructures, you want to do biofabrication, it becomes a real serious issue. We're talking about hundreds of megabytes of polygons, you know, and insane numbers of, if you're talking about voxels, these little teeny squares that represent physical structure in an MRI machine, you're talking about massive numbers of these that have to be processed. Validity and precision, cracks and approximations, and I'll show you a little bit more about that in a second. Parameterization and operability, blends, offsets, deformations. So if you want to really parameterize something, today you can parameterize. There's parameterized modeling is what they refer to it as. But it has limitations, so you can't just do anything you want. And often the software, even the most expensive software, used to be $20,000. I think now it's $5,000 in the US, here probably a lot more. But ProEngineer, for example, was notorious for simply failing and dumping your file if you tried to do something that you shouldn't. And you didn't know exactly what that was, always. So it was kind of a Russian roulette. Manufacturing and scale. Manufacturability and scale. So micro and macro in the same time. Obviously, if we're talking about a kidney, we've got this large structure, but as you heard today, we're talking about very, very small packages that we want to deliver inside that structure for doing biofabrication. And we might want to alternate cell types. So you've got a very complex, small structure in a large object. STL problems. So STL is the standard format that's used for 3D printing. It's a mesh format, like I showed you earlier with the sphere. It's just a bunch of triangles in space. So if you're talking about doing something very, very small details like this, the problems just become incredibly difficult. And so here's some of the issues that you see with surface representations like this. You have gaps, you have inappropriate intersections where they cross over, you have internal walls, and you have dangling areas, and inconsistent orientation. And this is very common in these systems. Let me show you a short video to demonstrate that. So this will be very fast. I've sped it up. So what I'm showing you here is something that's supposed to be a manifold. These objects are supposed to be one object. And if you notice here, this blend on the edge